Hi class, we're going to begin our series of lectures for Chapter 4, Variability. This is a term we've seen before. Again, back in Chapter 2 is where we first talked about variability. It's one of the characteristics of your data you can look at from your graphs. So variability, you may recall, the easiest way to think of the word variability is as the word differences. If we're asking about the variability in our data, we're asking if the scores in those data are very different from each other or not. I also said we could think of it as distances. How far apart are our scores? You got a score of 10, I got a score of 20. You got a score of 10, I got a score of 12. Well, are they closer together or are they farther apart? Are they similar or are they different? Again, I also like kind of using the word diversity, which is another way of saying differences, right? Are the scores all different from each other? There's a lot of diversity, or they're very similar. So we can have large amounts of variability in our data, small amounts of variability in our data. Under very unusual circumstances, we could have zero variability, meaning all the scores are identical, all the scores are the same. Not likely to happen often in the real world, but it can absolutely happen somewhere in the world of data. So what we're going to do in this chapter is, this is the first chapter where doing the math can mean a difference. Computations for a sample of data versus computations for a population of data. If we think back to chapter 3 with central tendency, the mean for a sample or mean for a population, the formulas were the same. We changed the symbol to denote which group it was associated with, sample or population, but the formulas were the same, only the symbols changed. The math is the same. Same was true of chapter 2. The symbols were changed for sample and population, but the math didn't change. It was the same calculations. We're going to see that that isn't always true starting in this chapter. So what we're going to do is we are going to talk ultimately about 3 ways of measuring variability. Just like we had 3 ways of measuring central tendency, mean, median, mode, we're going to have 3 types of measurements for variability. We're going to talk about range, we're going to talk about variance, and we're going to talk about standard deviation. Those are all 3 different ways of measuring the variability in our data. But we're going to have to sort of split it in a way that where we're talking about either populations or samples to keep the math straight. So before we get into those specifics, why would we use one or another? Any measure of variability, there's really kind of 2 goals at play here. So what a good measure of variability should do. First of all, it should describe the distribution. A measure of variability should describe the distribution. We said for central tendency that the measure of central tendency should be a good ambassador for all the data, a good representative. We're kind of saying the same thing here, that when I give you whatever that measurement is, that it should really adequately describe, fairly describe the data I have. So having a good description of that, of the distribution, is the first goal of a measure of variability. A second goal for a measure of variability is to tell us how well any individual score represents the whole set of data. So in other words, if I go into a set of data and I take one of those scores out, I should be able to evaluate, is this score like the other scores? Is it unlike the other scores? So if we looked at, say, exam scores, and I pull out your exam score, did you score like most other students? Did you score higher than other students, lower than other students? How much higher, how much lower? So that's the second purpose or second goal for variability. So the first, we just want to describe the whole set of scores in general. Secondly, we want to be able to take out any one score and look at it and say, how does this score stack up to the whole set? How does it compare to? Is it similar than, different than, those sorts of things. So that is what we're going through in this chapter as a whole, different ways of trying to reach those goals. Now, I said we've got 3 tools, and the first tool is called range. I'm going to be trying to be very clear about numbering, lettering things on the board here, because again, we're going to have to kind of switch back and forth between samples and populations. But where range is concerned, it's the same on both sides. Samples and populations, it's the same. Now, there are a couple of different ways of calculating range. But range tends to be the simplest and the most crude measure of variability of all our choices. It's the simplest and the most crude. We'll see what I mean by the most crude here in just a moment. But simplest, it's a simple tool. And so for me, I don't see a reason to try to make it more complicated than it needs to be. So we're going to go with the simplest way of all to calculate range. We take the highest raw score in our data, find the lowest raw score in our data, and subtract them. So if my data is this, well, my highest score is 12. My lowest score is 2. So my range is 10. Again, there are other ways of doing this that are a little bit more advanced, but that's all we really need. And so what it's describing is, in a points way, the distance, the difference between the highest score and the lowest score. What's the whole range? What's the whole spread here? Now, we don't use it that much. It's not all that useful for most of the work that statisticians do, but it is something that the general sort of population, the general public can more or less relate to. Compared to the other ones we're talking about, this is the most socially understandable one amongst just everyday folks. But again, it's simple and crude. What makes it crude? Why do I keep saying that? Well, we've got 1, 2, 3, 4, 5, 6, 7 scores up here. Out of all 7 scores, how many of them do I care about when I calculate range? Only 2 of them, the absolute highest and the absolute lowest. The rest of these numbers could be anything and it wouldn't make any difference. This could be 2, 2, 2, 2, 2, 2, 12. The range would be 10. But think about what the data is. Almost all of it is identical with no variability, 0 variability in it. There would just be one weird score sticking out there, where we'd have a hard time meeting that first objective of accurately describing the population. Here, that's a pretty good description. That gives us a pretty good sense of the data. Or let's just take it a different way. So let's see, 1, 2, 3, 4, 5, 6, 7. So now we've got 8 scores. Our highest score is 50, our lowest score is 2, so our range is exactly 48. But again, it doesn't do a very good job of describing this distribution. Almost all the scores are within 10 points of each other, and we've got this one what? Outlier or extreme score. We've got a skewed distribution. This would be positively skewed. The weird score is a higher score, positively skewed. So in this case, the range isn't really going to do it for us. So what we would do instead, there's a workaround for this called the interquartile range. I do on occasion see this in published research, so it is something that from time to time you'll encounter out in the real world. Interquartiles, well, quartiles, quartering. So what this says is we're going to compute a range, but first we're going to take our data and cut it into quarters, like quartering an apple. Well, what did I have? 1, 2, 3, 4, 5, 6, 7, 8 scores. So a quarter of 8, 8 divided by 4 is 2. So I divide this up into quarters. And it says I'm just going to use the interquartiles, the middle. So it says I'm going to take the bottom quarter and ignore it. I'm going to take the top quarter and ignore it. And so I'm going to simply compute the range with the middle. So it'll be the middle 50%. So the interquartile range here, 10 minus 6, is 4. So we could report the range as 48 points, but the interquartile range, the range calculated using the middle 50%, we took the top 25% and dropped it, took the bottom 25% and dropped it. This allows us to get rid of those outliers. This weird outlier, and if there were others and maybe on the other side, they just get dropped. We don't delete them from the data, we just don't calculate them when we're calculating the interquartile range. So that's interquartile range. It's mostly important that you know what it is. I'm really not going to ask you to calculate it much. Notice that I wound up with a nice set of 8 scores here. 8 is nice and evenly divisible by 4. What if there were 9 scores? The scores aren't evenly divisible into quarters anymore. The book will explain to you how to do that. But again, I'm not really going to bother with it. It's trying to get too fancy with a really simple tool, in my opinion. So I want you to know what an interquartile range is, so when you're reading research, you understand what they're trying to explain to you. But don't worry so much about calculating one. Calculating general range, everybody should be able to do that. But interquartile range, really more of a vocabulary word for us. So that takes care of range. We won't really need to talk about range again for the rest of this chapter. So as we move on from here, we're going to have to start being specific about, are we talking about samples or populations, and how to get these more advanced calculations done. So we'll start that in the next video.